Competitive sports captivate audiences globally and are renowned for embodying fairness and top physical performance. Yet the integrity of these competitions is frequently compromised by the shadow of doping, where athletes use prohibited substances to enhance their capabilities unjustly. During the Sochi Winter Olympics 2014, a new form of doping practice raised an issue called sample swapping, where some athletes replaced their doped urine samples with the clean samples of another individual to evade the positive doping test. Currently, the only way to detect such cases is through DNA analysis. However, implementing DNA analysis on all the samples collected from the athletes in competitions like the Olympic Games is a costly and time-consuming procedure that exceeds the budgetary limits of the World Anti-Doping Agency, WADA. Therefore, we need an adaptive model that can screen all the samples and flag the suspicious samples that require further investigation through DNA analysis. We developed a groundbreaking solution, SACNN, Self-Attention-Based Convolutional Neural Network. SACNN is designed to identify fraudulent sports behavior by analyzing athletes' longitudinal profiles. In doping tests, a longitudinal profile is a series of biosamples, like urine or blood samples, collected from an athlete over time. It resembles an athlete passport that tracks changes in various biological markers from multiple tests. These profiles help detect unusual shifts within the reference ranges defined for the particular athlete based on their previous samples that point to potential doping. SACNN has a novel model architecture and is the first to consider the longitudinal profile's spatial and temporal behavior in detecting suspicious doping activity in sports. It outperforms existing state-of-the-art models, offering a faster, more efficient, and cost-effective method of ensuring fair play. SACNN processes data through different components, including subsequence generator, attentional convolution neural network, and aggregate function. The subsequence generator generates fixed-length subsequences from the longitudinal profile, ensuring uniform data input. Attentional convolution neural network contains a 1D convolution layer that captures low-level embeddings from each subsequence. These are then processed through multiple SAC units, which combine self-attention layers, 2D convolution layers, and batch normalization layers to produce high-level embeddings, capturing intricate patterns in the profile. The self-attention mechanism helps SACNN focus on samples most indicative of doping. The convolutional networks allow the model to capture local patterns in longitudinal profiles, providing deeper insights than other machine learning methods. Finally, the fully connected layer classifies each subsequence as clean or abnormal based on the patterns recognized by the network. The aggregate function aggregates the predictions from all the subsequences to make a final decision about an athlete's entire longitudinal profile. SACNN combines subsequence analyses to consider overall patterns rather than isolated anomalies. This integrated approach makes SACNN far more effective than the traditional model and other state-of-the-art models. SACNN also employs adversarial training techniques, which involve continuously challenging the model with complex cases during training. This approach improves the model's robustness and ensures that it doesn't overfit the normal data seen during training, making it more generalizable and effective in real-world scenarios. Unlike the traditional adaptive model used by WADA, which employs the Bayesian approach, SACNN uses spatiotemporal data analysis to understand how different steroid biomarkers evolve and interact over time for a particular athlete. This is important for understanding complex patterns in these samples to identify sample swapping. Let us explore a case study on the performance of the SACNN in real-world sample swapping cases. We performed a blinded experiment with longitudinal profiles tested by the laboratory. These profiles consist of 2 DNA-proven sample swapping cases, 5 steroid doping cases, and 22 clean profiles. SACNN was able to successfully identify all the sample swapping and steroid doping cases. Here, spatiotemporal embedding maps represent high-level embeddings generated by the model. Each shows a subsequence from both clean and abnormal samples. Higher weights show a strong relationship among the 3 samples. The top row represents a clean subsequence and the bottom row shows an anomalous subsequence. The embedding maps evolve as we move from SAC Unit 1 to SAC Unit 4. Initially, the maps display broad features. By SAC Unit 4, these features are transformed into detailed patterns, highlighting critical data points that indicate doping. In the final stage, SAC Unit 4, the embedding maps are highly refined, focusing sharply on the most significant indicators of normal versus abnormal behavior. This precision allows SACNN to make reliable decisions on whether a profile suggests doping. In real-world tests using athlete profiles, SACNN has proven to outperform all state-of-the-art baseline models, demonstrating high accuracy and exceptional sensitivity at high specificity, minimizing false positives and unnecessary further DNA testing, which significantly reduces costs. With SACNN, sports authorities can more effectively combat doping, preserving the integrity of sports and the spirit of fair competition.